I would define the map psi of epsilon 0, 1, 0, 0.
Yes.
How would you map 1 though?
And psi of 1 would map to 1, 0, 0, 1. So this is, of course, the 2 by 2 identity map.
Yeah.
And this is a matrix that squares to 0. This is a nilpotent matrix of order 2. And so psi, and, so like psi of A plus B epsilon is, well, just what I've written there.
Yeah.
And you can multiply two matrices of that type. Yeah, no worries. You can multiply two matrices of that type and you'll see that you get the same lovely pattern.
Yeah. See, it just.
So yeah, if we have an algebra generated by one generator, it suffices to map the identity and that generator.
Yep.
That will be unique. Now I still have not proved that it's a isomorphism.
No.
I've proved that it uniquely defines the map, but I have not yet shown that that map is in turn going to preserve products. But it will.
It looks like you should be able to pop out the side of one term in like a normal algebraic structure, and then not put it into a matrix. But that might, just because it looks a certain way doesn't mean it is.
Yeah, well, I mean, I'm being somewhat lazy in my, this example, what I did was I found an isomorphism from the null numbers to their regular representation.
Yeah.
Well, is that the regular representation? I guess the regular representation, as I have typically defined it, might put B down here rather than up there. I mean, you could put B on the other side.
So it would change, the determinant wouldn't change, not that much.
That's a good, that's always something interesting to notice here. Which of these null numbers are invertible?
Yeah.
Well, that's easy to answer over here in B.
Yeah.
In that isomorphic version of null numbers, well, the determinant being non-zero is just going to be what? B doesn't even matter, right?
Yeah.
Just if A is non-zero. So anything of the form A plus B epsilon where A is non-zero has a multiplicative inverse. On the other hand, anything that's just straight a multiple of epsilon is a zero divisor. I mean, so that's the thing here. Epsilon is itself a zero divisor. This is an algebra generated by a zero divisor.
Yeah.
In contrast, like hyperbolic numbers are things that the generator was a unit, but by adding that unit or subtracting that unit from the number 1, we generated zero divisors. So the null numbers are a useful example because they challenge our usual intuition and yeah. Can I erase this bit here?
Yeah, I got that, but
I will go over. Can I erase to here? Just to there?
probably by the time we write that, I'll get all this done. Because I'm at that if B not is equal to 0.
Oh, okay. I'll just get up here then.
Yeah. B not equal to 0, then 1 is equal to psi minus bk plus that. Bn, kn over b naught. And then this is the example. very solid.
So I'm still working in the algebra of generator K. All right, where the algebra it's an n-dimensional algebra. All right, and I want to prove now to you that
The isomorphism exists.
that the isomorphism that we defined necessarily preserves the product in the algebra. We already know that psi is uniquely defined by mapping the generator and the identity. I'm currently using the notation, as we often do, that k to the power 0 is by definition 1. Right, and here the ci and the bj, these are all real numbers, because that's what it means for the algebra to be generated by k, is that any algebra element can be expressed as an n-fold sum with real coefficients and powers of the generator. Really is an n minus 1th order polynomial in the generator. This is, of course, a special class of algebras. There's algebras that you need more than one generator to generate. Okay, like we're focused here on really a special subset of algebras at the moment in our initial discussion. You know, we can have algebras that are built from more generators that are not nicely related. In fact, we've already looked at those. The direct product algebra, for example. Well, never mind.
Yeah, I think we can strictly just one generator.
Yeah. I should shut up. If the algebra is isomorphic, if two algebras are isomorphic, right?
Yeah.
And one of them is generated by a given generator, then the image of that generator will serve as a generator for the other algebra. So, okay, so z times w and a, right?
Yeah.
That's this polynomial times that polynomial.
Yep.
The way the algebra multiplication works is that we just, combine products. Like essentially, it follows essentially from the rule that k times I, k to the I times k to the j is k to the I plus j, right? And in short, what we have here is the sum over I and j from 0 to n minus 1, the real coefficients out front, and then k to the I plus j, like that. See, because k to the I times k to the j is k to the I plus j, and I'm using the distributive property to collapse the sums. To collect the terms together like that, right? So this is assuming the distributive property and essentially the definition of the generator. Well, definition of the exponential notation, I suppose, which is among other things, k to the I times k to the j is k to the I plus j. Now,
but wouldn't the k's can only be additive and only if I and j are equal to each other?
But like, for example, the 3 hyperbolic numbers, we had stuff like j to the 1 times j to the, j squared is j cubed, right?
Yeah.
It was also equal to 1, but we could have left it as j cubed for an intermediate calculation,
okay. Yeah.
So then, by the definition of our map, we extend linearly and across products, which means that I can pull the sum out. I can pull the constants out. And then I have psi of what? K to the I plus j, right? Well, but psi of k to the I plus j, but let me just get to the point here. Fine, I'll write more. But then, so that's by linearity. And then by our product extending rule, what do we got? So I can pull the I plus j outside, right?
Yep.
And then I'm going to just do one more step, which is to rewrite it as psi of k to the I times psi of k to the j. there's an in-between step I didn't bother to, I'll write it here. You know,
Oh, yeah, no.
and then I split it, and then I will undo the distribution and put the sums back to their, write them separately. So Ci, psi, k, Li. Then of course I can pull the sum back inside, use linearity in reverse. I meant to bring the k to the power I inside.
Oh, okay. I mean, but that's a good point.
Yeah, I mean, which step how many steps do you want to do at once? I guess it depends on how big a board you got, right?
You can erase under you whenever you need.
Oh, thanks. I need. Did I actually finish making coffee? I think I was talking about making coffee, and yeah, the funny thing is, unless you actually put the coffee into the coffee maker and hit the button, it doesn't count.
I used to always have to remember to do that for my mom. Even though I just got some coffee before I came here, never been like the biggest coffee drinker.
This is the thing, is like if I need to make coffee, I'm slightly sleepy already, and then it's just a bad situation because the things that I need to be did,
Yeah.
There we go.
Also, my mind was like, I should really text Carson and Maya that all the summation questions that we had. I was like, I finally get it now, but it's kind of too late to like explain it to them.
It's funny. So this is psi of z, psi of w. So that, yeah, I mean, it's just.
I don't know why, like I knew that's where you're heading to, but it still was cool to see it.
Right. And of course, you could do all this without the summation notation in a particular example, but the steps are always basically amounting to this. But yeah, so this is why our strategy today to define the isomorphism, you can't go wrong.
Yeah.
All right.
Did you also get you could also pull constants out of it? Because isn't that one of the things?
Well, yeah, essentially that's part of our construction is we extend linearly.
Okay.
So this is a linear algebra thing. If you, well, I guess to put things in order, I should define the mapping on the basis, and then I should extend linearly. So, just to be clear, like H2 has basis 1 and j, Those are linearly independent spanning set over the reals. And so if I say psi of 1 is equal to Pac-Man, right? And if I say psi of j is equal to ghost, even though those are just two values I've defined for psi, that has a unique linear extension.
Yeah.
So, for these algebra with a generator of order n, if I define psi of 1, psi of k squared, psi of k cubed, psi of k to the n minus 1, I've defined psi on 1, k squared, k cubed, all the way on out. That is a basis. I mean, that's the critical thing that I should really fess up to is if I say that the algebra is generated by k, like that, that means that the set 1, k squared, k to the power n minus 1 this is a basis for the algebra of dimension n. Not all algebras can be presented as such, but we'll get a lot of mileage out of these kinds of examples.
Yeah.
Right. So can I erase all this?
Yep.
Let me go back to your mapping, because I think your mapping, I think you got it. Right, but let's see if we can be slightly, there's got to be a way to write it more compactly, kind of. It's funny, the research project Bill's been tinkering around with for the last few months. It is loosely related to the course I'm teaching you in the fall.
Number
So,
3?
Yeah.
You can erase those two.
Oh, yeah, I should do that.
Then erase them all out.
I should leave that. What's happening?
You grab some scissors.
Oh, okay. Really? Are you sure? Yes? Oh.
RCQ.
Going fast, huh? Some guy driving kids around in a car or something. I don't know.
So for h3, will we need a z cubed?
For the quadratic equation?
Yeah.
No, it's still a quadratic equation.
Even without a z cubed?
Quadratic. I mean, so, all right, so this is, first of all, this is a question of nomenclature. Like, I will use this zeta for x plus jy plus j squared z for like a variable in H3,
Mm-hmm.
right? And so like, maybe it's good to have some notation. Maybe we should say H3 is, and it's really, it's j such that j cubed is 1, right? Anyway.
Okay.
I don't know, I don't really use that notation. Maybe I think it's probably better to just be more explicit so students aren't lost as much. But yeah, fine. Then the so alpha zeta squared plus zeta plus gamma equal to 0. That would be the quadratic equation in H3. Now, but the thing is, that's going to correspond back, for a, let's say, now did we do C cross, yeah, we did C cross R, so that's going to correspond to something like, versus I almost. Well, so I'm going to do x1, x2. I'm sorry, Audrey. Let me stop that. I have trouble making choices, you know.
Show you now. Let me show you now.
What are you going to show us?
Let me show you something.
Okay, show him something.
Show me.
Okay.
All right, I guess we're going over there. The thing is, if we don't, we'll not get his piece. What were the measures?
Solution.
Oh. Oh, yes. Space there. Oh, that is pretty cool.
Yeah.
Because that's something you could do for relatively little money. So there's like a course. Well, now I'm having trouble not
Brute force it.
reusing the same notation again. But so for that reason, I'm going to go back to x1, x2, x3, mostly so that I can write without ambiguity. Down here, there's something basically of the form, you know, az squared plus bz plus c, comma, golly. Let's say, I don't know, a bar t squared plus b bar t plus c equal to 0, 0.
C bar.
Thank you. I don't know if this is a good choice of notation or not, but
So why do we need a 0, 0 for? Oh, okay, no, never mind. I'm with you now.
and this is 0.
Yeah, because you're setting it equal to both.
This is C cross R, so this is more, you know, and so here A is equal to like A1 plus IA2, B is equal to B1 plus IB2, C is equal to C1 plus IC2. Here, A bar, B bar, C bar, elements of the reals, and here T is a real variable. Whereas here z is x plus iy is a complex variable.
I didn't even think about how, I totally forgot how we don't have symmetry.
And yeah. No. Let me talk to you a couple minutes about how to solve complex equations. Yeah.
Okay.
So I'm going to tell you a little bit more than we need because I know you haven't hit complex variables yet, and this is just a little bit of like complex algebra that we could teach pre-calculus, but we don't. It's okay. And once you know this, it justifies the solution to the quadratic equation. So anyway, we get to it. So let's say omega is equal to, omega sub n is equal to exponential of 2 pi I over n. All right, so this is the so-called nth root of unity. It's an nth root of unity, which means that, you know, omega sub n raised to the n power is equal to 1. And yet, 1 omega n squared omega n to the n minus 1, these are linearly independent. Well, I say linearly independent. I shouldn't say linearly independent. That's the wrong thing to say. They are distinct. They're complex numbers, so you can't take more than two of them, which are distinct and have linear independence. Because complex numbers is R2, so you can't have more than two vectors in the two-dimensional vector space, which are linearly independent. Anyway, so there you go. And any complex number, right? You can write as in the form the modulus of the complex number times e to the I theta, where theta is an element of, let's say, minus pi to pi included. Okay. Typically, theta is called the principal argument, or arg, of z. Principal argument of z. And furthermore, we can define the principal nth root of z. Okay. So the principal nth root of z, which this is the notation that's used for it typically, the nth root of z, it's equal to the real nth root of the modulus of z. So this here is the square root of x squared plus y squared. Yeah. And then you have e to the I theta over n. Here n is a, typically 2, 3, whatever, it's like that. It's a natural number.
Yeah. Then just. Okay.
For example,
Yeah, no, I'm with you now.
for example, the nth root of 1 is e to the well, what is
Wait, why would you have the n on the? Wouldn't it be the length of z to that cube root, but the e wouldn't that just have the I theta? Why would you have the n there? Why would it be over n if you're multiplying it by that 1/3?
Oh, I'll explain that in just a second. But for example, the principal nth root of 1 is e to the 0 times I to the 0 over n, which is just 1. It's like the principal nth root of 1 is just 1.
Yeah.
And in fact, the principal nth root of any real number is just the usual nth root of a real number. It's like so like the principal cube root of 8 is still 2.
Yeah.
All right. Now, why this?
Mhm.
This, it solves w to the n equal to z. So try it out. So I set w equal to the nth root of z. So I have the nth root of z, modulus of z, times e to the I theta over n raised to the n power. Now, properties of complex arithmetic. So this is a real number times an imaginary exponential. And so that is, that gives you the nth power of this real number, and then times the nth power of e to the I theta over n. But you can prove by induction or whatever that this is e to the I theta over n times n. The n's cancel,
Mm-hmm.
and you get I theta.
Yep.
Over here, you just get modulus of z.
Yeah.
So you get modulus of z e to the I theta, also known as z.
Yep.
So this is a solution to this equation. It's the principal nth root. Now the theorem is that Wn equal to z has solution set. Here goes. The principal nth root of z. All right. And then you can do omega n times the principal nth root of z. And then omega n squared, principal nth root of z. All the way up to the n minus 1 power of the principal nth root times the nth root of z. These are the n solutions to this complex equation. For what it's worth, it also tells you how to factor the polynomial w to the n minus z.
Mm-hmm.
Now, let me make this like less esoteric. Let me actually show you how this plays out in a specific example. So like what are the, you know the cube root of 8 is
3 or 2.
Is 2, right? So I want to find all the equations, all the solutions. I want to solve w cubed equal to 8.
Do the same thing w equal to 2.
So,
Or minus.
by the way, this one other thing I forgot to tell you is down here we have a name for this set. This is defined to be z to the 1 over n. So in complex analysis, we make a distinction between the principal nth root and the set of nth roots, because there's more than one nth root.
Yeah.
So it's useful to distinguish that notation from that notation.
Yeah, that makes sense.
In real pre-calculus, we just distinguish the, we joyfully confuse these to confuse the students. It's not hard. Now, so I want to calculate what are the, what's the third roots of 8? So to say that w cubed is to say that w is an element of the cube of the third roots of 8.
Yeah.
Now I know that that's the third root of 8, comma, omega 3 cube root of 8, right? Omega 3 squared cube root of 8. Which of course in this context is 2 omega 3, 2 omega 3 squared. Of course this omega 3 is the thing you've been playing with, which is exponential of 2 pi I over 3. Which, if we take a more geometric approach, we can kind of see what that is, right? So you're like, this is like, let's see here. Like pi over 3 takes you 60 degrees over, right? And then this is 2 pi over 3 over here, right? So it's 30 degrees off the y-axis. It's more up than it is over.
Yeah.
So the formula for this is actually minus 1 plus I root 3 over 2. Because the sine of Well, yeah, because the 30 degrees is here, so the sine is the, anyway, so that's that. But omega 3 squared is actually equal to omega 3 conjugate, right? It's the same thing, but it's down here. You know? And of course, 1 is back over here. So if you add these, add the 1, the omega 3, and the omega 3 squared, you get 0, like I talked to you about the other day. Yeah. But this is minus 1 minus I over 3 over 2. So my point to you is just that if we have a complex equation, right, and the complex equation comes out to like, you know, w to the n equal to blah, right? We can solve that equation.
Yep.
The equation has n solutions. They're just w equals w. Well, w is an element of the set of nth roots of blah. So when I solve the quadratic equation, if you solve the quadratic equation in the complex, you can reduce it to the problem z squared is equal to a complex number. Well, z minus something is equal to a complex number. Z minus something squared is equal to a complex number, and then the 1/2 power. So that's the question: what does this look like when n equals 2? N equals 2 is the thing you talk about that you liked, right?
Yeah.
E to the pi I, also known as I, right? Because, oh wait a minute.
No, I thought Euler's equation was.
Oh, I'm wrong. That's not pi. What is it? E to the pi equal to what? I can't do math. You shouldn't do math once. -1, very good. Because cosine pi is -1, sine pi is 0, I times 0. Great. So if I have, like, w is an element of, say, I don't know, 1 plus I to the 1/2 power, what does that mean?
You square the whole thing.
Right, so it's like, this is
Not square.
the principal square root of 1 plus I,
Yeah.
right? And then omega 2 times that, which in this case is minus. So it just so happens that when you take the square root of a complex equation,
You get 2 solutions.
there's 2 solutions, and they're just plus minus.
Yeah.
But that's not just assuming that the real algebra extends to the complex numbers without thinking. Like, that is part of a more general story of how to solve the nth, you know, like the power, the nth power problem. But yeah, it just so happens that when we have something squared in a complex equal to something else, when we take the complex square root of both sides, it just amounts to getting plus or minus the principal square root. The principal square root, in this case, 1 plus I, that's the square root of 2 because that's the length of 1 plus I.
Yeah.
1 plus I is here. So the argument, pi over 4. So this is e to the pi I over 4. And so when I calculate the principal square root of 1 plus I, it's equal to, you know, the square root of the square root of 2.
2? Oh, no. 1
Yeah,
4.
2 to the 1/4, but that in our current context is bad notation. You know, like, and then e to the pi I over 8. In other words, the 4th root of 2 times e to the pi I over 8. There you go, that's the principal square root of 1 plus I.
But wouldn't, no. Yeah, no. Okay.
So the basic principle here is that to calculate products and roots in complex number system, the easiest path is to find the polar form of the complex number and use theorems that are known for that. Because that's all this is really saying, is like, to find the, nth root, the principal nth root of the complex number, we find its polar form, which is this.
Yeah.
We take the regular, plain Jane, real nth root of the modulus of it, the real part, the length of it, the magnitude of it, and we simply divide the standard angle by n.
How do you get that from the polar form? Because isn't the polar form cosine theta plus I sine theta?
Well, that's what e to the I theta is.
Yeah.
I mean, in real notation, this is length of z, cosine theta, length of z, sine theta. So, given current political discussions, it is amusing that this is also
I don't know if you can post this on YouTube anymore. I don't think I've ever been a good video.
I didn't start this. I mean, I personally think that e to the I theta is really the normal notation. You should say cis theta. Anyway. It's cosine and sine,
Yeah.
But I never use this notation. I like e to the I theta.
Yeah.
I don't like this cis notation. Sorry. Let me erase that. So, oh, okay, so going back to the, can I erase all this?
Yeah.
In my baby algebra, what's it called, intermediate algebra course in the fall, I somehow found myself cubing that number. I cubed that number as an example of complex arithmetic to show that it worked back out to 8.
Well, they would just believe you.
I know, but we actually multiplied it out, mostly just as an example of complex arithmetic.
Yeah.
And then I realized what class I was doing it for, and then I felt
Evil.
it felt wrong. It's like,
Yeah.
it's just not the right place. Anyway, okay, so complex, we have az squared plus bz, and so this is probably what we saw, right? So if a is not equal to 0, so first of all we do z squared plus b over a, z plus c over a equal to 0, and then this is
Complete
z
the square.
Yeah, complete the square. Minus c over a minus b squared over 4a squared, also known as, I have to add it actually.
Yeah.
So also as b squared minus 4ac, all divided by 2a quantity squared, right? And then so I've got complex quantity squared equal to that, which means that z plus b over 2a is an element of the
Yeah, okay, yeah.
and that's to say that z, and that actually, because of how the half roots work out, that means z is equal to minus b over 2a plus or minus the principal square root of b squared minus 4ac over 2a squared. Okay. All of these numbers can be complex.
Yep. Yeah, it makes it a lot simpler to solve the principal thing.
Right, now all these numbers can be complex, and when these are complex, like when A, B, C are complex, it doesn't have to be that these come in a conjugate pair. Now when A, B, C are real, that makes this either equal to minus 1 times a real number, it's either a negative number or it's a positive number or it's 0, right? If they're all real.
Mhm.
So if these are real, then this works out to either, a conjugate pair.
Yeah.
But when A, B, C are complex, all bets are off.
Mhm.
Because you can write down a complex equation like this. There you go, complex polynomial equation. The solution is 3 minus I and minus 2.
Mhm.
Those are not in a conjugate pair.
No.
But when you multiply this out, why did I make this example so complicated? 2 minus 3 plus I, guess it's not that bad. As you can see, the coefficient, well, A is 1, but B and C are complex coefficients, so But nevertheless, this calculation is general.
Yeah.
There are always two possibly distinct solutions to the quadratic equation for complex numbers.
I don't know what's wrong with that.
So I heard a professor, not when I was a student, but when I was a professor, say something like, "Oh, students just take plus or minus. They don't even know what they're doing." And I was like, "What do you mean by that?" And then you can't just, that kind of person, you can't just ask them directly. They'll lose all respect for you as a professor, right? So I'm just like, I don't know what they're talking about. When I solve quadratic equations, I just take plus or minus. Like, what's the problem? Well, the problem in their view is that I was assuming that see, in the plus or minus thing, in the real, it derives from the factorization of 0 lemma. Like the fact that if you have product of two real numbers are equal to 0, either one or the other of them is 0.
Yeah.
So if you complete the square on a real polynomial, real quadratic, and you get that, when you complete the square on the real quadratic, you can then write it as a product of, you can use the difference of squares to factor it. And then when you have that factor product equal to 0, it stands to reason that either one or the other of them is 0 if there's going to be a solution. And that straight away leads to the quadratic formula with the plus or the minus in it. Right? What is a leap of faith is assuming that calculation still makes sense when those numbers are complex. Because, it's not. It does in fact still make sense, but that's because complex arithmetic is actually quite beautiful.
I think for lower level algebra, I don't think it's that big of a deal. But for what we're doing, yes, very big deal. That it's not conjugate.
Oh, yeah.
And also is, I don't know why, but I feel like it links somehow. Well, no, that's away from the point now, because this is just general analysis or algebra in the complex system.
So we'll see the nth roots of unity come up a lot
Yeah.
in your next course. Like it's kind of bread and butter. All right. Getting back to your map at last. Can I?
Yeah.
All right.
I got everything.
So good news. We can solve real quadratics. We can solve. In fact, once you solve the complex quadratic, you can say, well, every real quadratic is a complex quadratic, right? So if I can solve the quadratic, I solve the real. That's kind of cool. Turn the tables on them, And okay, so you've got f of h3. Okay, so f of 1 is 1, right? And we said f of j was, what was it? E to the, let's call it omega. So let's let, for the sake of not going nuts here, let's let omega equal to exponential of 2 pi I over 3, right? Now, some math for you. So here's the thing. Of course you know that omega cubed minus 1 is equal to 0, right?
Yeah.
This factors to omega minus 1 times omega squared plus omega plus 1 equal to 0.
Yeah.
Now, is omega equal to 1?
Yeah, it could be. Well, yeah, that's right.
It's this, so it's not 1.
Yeah.
Omega is not a variable, omega is this fixed element. So, since omega is not 1, let me take a step back here. So, to try to unconfuse you, if we had the equation lambda minus 1 times lambda squared plus lambda plus 1 equals 0, right?
Mm-hmm.
There are two solutions to that equation,
Yeah.
at least two. One of them
Yeah.
is lambda equal to 1.
Yeah.
The other one is lambda equal to omega.
Yeah.
So, in fact, it's the case that omega squared plus omega plus 1 is equal to 0.
Yeah, because we have omega not equal to 0, no 1.
Now, I mean, there's other ways of understanding this. This has to be 0, because you can also understand it geometrically, right? It's the sum of 1 is here, omega is here, omega squared is down here, right?
Mm-hmm.
So when you add those up, you get the middle. Because we're adding up the third roots of unity. So all I'm trying to say is we do have this to play with. Simplify formulas.
Yeah.
That's all I'm saying. So f of j was omega 1, right?
Yeah.
And f of j squared,
Omega squared.
omega squared times 1, right? But if we don't like to work with omega squared, we do have the freedom, we could trade that for minus omega minus 1, 1. That might be helpful. I don't know. Just saying it's there. Now the formula, oh, yeah, there's. So what do we want? We want f of blah, 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 blah.
A plus bj plus c
Okay.
j squared.
So that's, I'll write it out, a times 1 to 1, plus b times omega 1, plus c times omega squared 1, which is a plus b omega plus c omega squared, and then a plus b plus c.
Oh, that's nice.
Mm-hmm.
Wait, so the only quadratic we're solving is in the complex? Like we wouldn't even have to solve quadratic.
Oh, don't, this is just the map. We're not to the quadratic yet.
Oh, okay.
Now here's a nasty question.
Okay.
Because if you think back to our discussion, we really do want to know the inverse map to fully understand the story we're telling. What is the inverse of, I guess x plus iy comma t,
Yeah.
Well, I guess we can figure that out. That's f and it's still a linear map, right? So it's got to be f times f inverse. Oh, see, here's the problem, right? We don't actually know what maps to 1, 0, what maps to 0, 1, or what maps to I, 0. Like, if we did know those, then...
But no. Can't you pull out a 1, 1, maybe? Or am I tripping?
If I had x and t matched up, right? I guess I could, play some games. But you know what? I'm just saying, that direct approach, I kind of unless I'm more clever on a given day, I get stuck there. let's use a base, like, okay, so, C cross R, we can use the bases 1, 0, I 0, and 0, 1. We can think
Yeah.
about those. We can think about C cross R as R3 really, where this is my E1, this is my E2, this is my E3, with that understanding.
Yeah.
And with that understanding, shoot, I mean, see, I can't help but get complex here, right? Like, I mean, this is A plus B times, what's omega? Well, omega is -1 plus I root 3, right?
Yeah.
Over 2 plus C times -1 minus I root 3 over 2. A plus B plus C, right? And so that is it is 1, 0 times what? Times A minus B over 2 minus C over 2. That's the real part of the first component. I really should put this, write this over here, sorry. And then, what's the imaginary part? Well, we got what? B root 3 over 2 minus C root 3 over 2. That's it, right? In terms of imaginary parts. Times I 0. And then finally you got your A plus B plus C times 0, 1. Remember, this is E1, this is E2, this is E3, so you could stack them, you know. Just, this is
3, 2, minus C root 2. That wouldn't leave that I 0, and then the 0, 1 plus, yeah.
right, so this is, again, this is a 3 row by 1 column, 3 by 1.
Yeah.
And now we can write the matrix of this map.
And then we're taking A, B, and C out. So we get 1, we're doing a 3 by 3,
Mm-hmm.
minus 1 half, 0,
Mm-hmm.
3, root 3, 2, minus root 3, 2, 1, 1, 1. And then by the column ABC.
Yeah, so there's the matrix of the map with respect to that, you know, natural choice of basis here. So F inverse,
Just the inverse of that.
we could invert that matrix, and that would give us the formula for the inverse.
Yeah.
Of course, we also, I mean, I can tell you some things without any work, like F inverse of 1, 1 has to be equal to 1, you know?